Hopefully, if you are attending, then you already know who I am. I'm Amit Kuber from IIT Kanpur, and I will talk about representation theory of quivers. Uh, so basically, currently, I mean, officially, I'm the only person working in this area in our entire country. So that's why it was my wish to deliver a course on this topic, and that is the reason why this is happening. Perhaps so the I'm going to say something motivational, no, sorry, motivational is different. Motivation of the subject I will share with you today, and then we will go on to talk about some details. My lecturing style is going to be slightly different than what you have observed so far, uh, because I want to cover a lot of ground. Yeah, there are several topics which I would like to introduce to you. And because I certain things were probably not covered in the last week, I have I have to talk about a lot of things. So the way I'm going to proceed is I have already prepared some notes, and those notes I will talk a lot and write less. But whenever I introduce a new concept, then I will simultaneously talk about an example. Yeah. And there are some parts of algebra, like if you remember Upendra, when he started, then he talked about this representation theory of quivers being linear algebra on steroids. However, I'm going to present a slightly different point of view. If you have studied algebra, let's say commutative algebra, rings and modules, that kind of stuff. So my approach to this course, to this subject is like that. Yeah, from algebraic perspective, like abstract algebraic perspective and not linear algebraic perspective. And I'm mainly interested in combinatorics. So we will also see some combinatorial flavor, some pattern recognition and those things. The main book I'm going to follow is this Ralph Schiffler's Quiver Representations. You can see that on your screen, I hope. Yeah, so that book is what I'm going to follow mainly, but there are certain topics which I want to cover from this book as well. Yeah, Elements of Representation Theory of Associative Algebras by Assem, Simpson, and Skoronsky, and only volume 1. Yeah, volume 2 is more advanced. Even I don't know enough about that, so only volume 1. And I have put both these books in the folder. If you remember Upendra Kulkarni's folder. So I don't have access to that folder. I'm not the owner. So I have put it in additional material because I could add it there. And my notes are, they look something like this. Yeah. Okay. So I'm going to talk a lot and you should stop me a lot. It should be a conversation. What I have seen in the past week is that all of you are very polite. Yeah, you first unmute yourself and then ask, can I ask a question? And then you ask a question. So directly stop me. Yeah, you don't have to worry at all. Just start talking. Yeah, because I want to make sure you understand things. Okay, so so far what we have seen a definition of a quiver, and I'm going to talk about its representations only on an algebraically closed field. Yeah, that's my first line, k equal to k bar. And the category of k representations of a quiver, I'm going to write it with rep kq. I'm going to emphasize on k and with capital R. So this is the category of representations and morphisms. If you don't know what categories are, then a quick introduction would be that in mathematics, you do not study any object for itself. You always study an object in conjunction with another object, in conjunction with morphisms between them. And those morphisms normally preserve the properties that it is supposed to preserve. Okay, so as simple as that. So categories, category of representations means representations as well as morphisms between them. So we have to talk about the home sets in those categories. And the category of finite dimensional representations, yeah, that I'm going to denote by small rep kq. The R is small here. And both of these are actually abelian categories. Now, if you have never seen the definition of an abelian category, then it simply means that there are direct sums, finite direct sums are allowed, kernels and co-kernels of all morphisms exist. And if some certain morphism is injective, then we then it is a kernel of its co-kernel, and if certain morphism is surjective, then it is co-kernel of its kernel. Yeah, something as simple as that. Yeah, I will make one more announcement, the same announcement once again. If you want to show your
What was the last
faces,
statement which you said? If
I will
a
repeat it.
morphism is injective, then
If a morphism is injective, then it is the kernel of its co-kernel. And if a morphism is surjective, then it is the co-kernel of its kernel. Okay, that is the definition of an abelian category, basically.
I'm sorry, I'm getting confused a bit. But when you're saying a morphism, that's an arrow, right? And when
Yeah,
you're
yeah,
saying
an arrow.
kernel and
Yeah.
co-kernel, these are objects in the category.
No, kernel and co-kernel are also morphisms, injective morphisms and
Okay, you're
surjective
talking about kernel
morphisms.
and co-kernel as a morphism over there. Okay, okay, okay,
Yes,
okay.
yes,
Thank you.
yes,
Yeah.
yes.
Okay.
Okay. Yeah, so if people want to show their faces, yeah, that would be great, because then I will feel like I'm talking to an actual audience rather than this, just an empty room, and I can already see some faces, so thanks to them. Okay, so representation theory for me is something like this. Yeah, if you try to understand a three-dimensional object through various snapshots of this object. Snapshots are two-dimensional objects. So basically, you can only see some parts of it. And then you are trying to describe some properties of the three-dimensional object by looking at the two-dimensional pictures. So normally when you are thinking about a ring, yeah, ring has got two operations. One is addition, the second one is multiplication. And the multiplication operation is, I mean, makes it complex, much more complex compared to our normal abelian groups. Abelian groups and vector spaces, they are much easier to understand. So therefore, a standard practice in mathematics is that you start with something which is complex, and then you look at its shadows in something that you understand very well. And that category where you are looking for shadows is the category of vector spaces. And those are your representations. And somehow you are hoping that by looking at all its shadows, you can understand the object itself, the abstract object itself. Okay, so that's how we are thinking about this particular problem of representation theory. And once we want to do representation theory, then the first thing would be that classify all the representations. That's our main classification problem. In whatever representation theory you study, you have to classify all representations. But usually classifying all of them is a really hard problem. So instead of that, you settle for classification of finite dimensional, finitely presented, finitely generated. At least can we classify that? So that's our first classification problem, that can we classify all objects and maps of the category of representations. Yeah. And in as far as objects are concerned, yeah, this category, the category of representations has a very nice property, namely the Krull-Schmidt property. So what it says is that given any representation, you can write it, I mean, a finite dimensional representation, you can write it as a finite direct sum of indecomposables. Moreover, this kind of decomposition is unique up to isomorphism. How can we do something like this? The idea is simple, because we are talking about finite dimensions. You use the idea of induction. If the object, the given representation itself is indecomposable, well and good. Otherwise, it's not indecomposable, so it decomposes. Then you ask for both those parts, are they indecomposable themselves? Otherwise, you keep splitting it, and because the dimension is finite, eventually you are going to run out of things to do. And for uniqueness, you have to work a bit harder, but Jordan-Holder theorem will help you over there. Any questions so far about this Krull-Schmidt property? Okay. So if we are talking about classification of objects as well as morphisms, then what exactly are we looking for? So morphism should also factor. Now, you are parallelly studying Lie algebras in the morning sessions. In Lie algebras, I don't think people have gone up to that because classification of objects itself is a very hard problem. Whereas this problem is relatively simpler. The representation theory of Quivers is relatively simpler, and therefore Krull-Schmidt property says that if you classify all the indecomposables, then you are done with the classification of objects. However, you still need to classify all the morphisms. So how do we classify morphisms? Well, here is the notion and with an apt name. Yeah, this is an aptronym, irreducible morphism. So you say that a morphism is irreducible if, first of all, it doesn't have either left inverse or a right inverse, which means it is not a split morphism. Okay? It's not a split morphism, and if at all it factors, then if at all it factors like f is equal to hg, then either g is a split mono or h is a split epi. See, any morphism, we cannot stop it from factoring. If you have a morphism from x to y, you can always go to x to z, x to x direct sum z. X direct sum z is a direct, x is just a direct summand, so you embed it there and then you ignore that z. That z plays no role in the factoring process, but still the object is more complicated. So you always have this possibility that you can factor. So what we are removing, a morphism is irreducible if it doesn't have any non-trivial factorization. These trivial factorizations we do allow. Okay, so see, existence of such non-trivial morphisms itself is a very strong property, but we are still asking for it. Okay, so we'll see that in the representation theory of Quivers, we will indeed have such morphisms. Now comes the first result.
Can you recall split mono and split epi?
Split mono means it is a, okay, so monomorphism is injective morphism, which has one-sided inverse. What side inverse? Like there will, so F is a mono, a split mono, if there exists G such that G composed with F is identity. Yeah, and epimorphism is surjective morphism. Like the category theoretic language is stuck on my tongue, so I will continue to use that. But just think about inclusions and surjections. Yeah,
oh, that's fine. Thank you.
Okay. Right. So these.
So did you mean
yes.
that it is? Did you mean that it is? It does not have two-sided inverses, or
it may or may not have two-sided inverse, but it at least has one-sided inverse. That is a split morphism. Yeah, all isomorphisms are split.
Okay. No, I mean is so from in the definition there are two parts, right? First one says it is non-split. Second one says if there is a this thing, then it is either split mono or split epi. Is this a one or two condition or one and two condition?
One and two condition.
Okay, so it does not have two-sided inverses, and if it has this commutative diagram, then it has at most one-sided inverses, like it is either an epimorphism or a endomorphism, monomorphism.
Yes.
Okay, thanks.
Okay, so these are only the trivial factorizations. Yeah. So the concept of irreducible morphisms is really
so this splitting is exactly like how we have splitting in short exact sequences, right? I mean, which is to say Z would be a sum direct sum in which one part is the image, the other part.
No, it's slightly different. Yeah, maybe I will share another window. I have something else for writing. Maybe I'll share another window and then I will show it to you there.
Okay.
Can you see this? Yeah, can you see my whiteboard? Yeah, okay.
Yeah.
So
Yes.
I have this space to write. Okay. So basically what I'm talking about is this. Yeah, if I take this x and y, then one type of factorization is I go to x direct some z, and then I have the first inclusion. What is the map? It is 2 cross 1 map. So basically it is identity on x and then 0 map. Doesn't matter. And then this map is my f. Yeah, this is my f map. This is my f and the other map is 0. It always factors like this. And similarly, it also factors like this for any z. Yeah, you have y direct some z, and then this is the this is the identity on y and comma 0. And here you have a map which is f and 0. So as you can observe, this one is a split mono and this one is a split epi. So these factorizations always exist for any z. This is what I'm talking about.
Okay. Thank you.
Any other questions? Okay, so I will
What
go
do you
back
mean
to
by
the other.
split then?
Yeah.
What do you mean by split then? By split, what do you mean?
Okay. I will write that again. So
Yeah, do you mean that by split, it is just the split of the morphism F in some sense?
yeah. See, F is a split mono if this happens. There exists a G such that G composed with F is identity on X. The dual version is the okay, so split mono, I think it's called a section. Those who know topology, and the split epi is called a retraction. Does that make sense? My first page somehow is not printed here properly, so therefore I'm going to again go back to the PDF for some time, and then I'll come back to this. Okay, so irreducible morphisms, I'm saying that they are either a monomorphisms or epimorphisms. That's our first theorem. Yeah. So given any morphism, let's say a function, can you think of a way to factor it? A canonical way to factor it? This is simple set theory. Does it always factor like something? I think you know. If I, yeah.
Into its image and the image being included in
Very good, very good. Yes. So image factorization, right? So maybe I will, because only one person answered, maybe I should go back. And this I'm only doing right now because of some technical problem. I'm switching between these two screens, but okay. So suppose x to y is irreducible. Yeah. Then we have this thing, which is this is a surjection onto image of f, and then there is an inclusion. Yeah, this is the standard image factorization. Now assume, so f is irreducible, okay? F is irreducible. Assume that f is not surjective. Now this is G and this is H. Suppose f is not surjective. Then what can you say about H? Can H be surjective? Because x to image f Yeah. X2 images. Suman, you want to say something? You have unmuted.
No, it's not surjective.
It's not surjective. Okay. So F is irreducible means there are two options. Either G is a split mono or H is a split epi. Correct? So if H is a split epi, yeah, I mean, this is a simple exercise, then it is an iso. A split epimorphism, which is also injective, is actually an isomorphism. Yeah, this always works. Which is a contradiction because we have assumed that it is not surjective. And therefore, what must happen? So a contradiction. Therefore, G is a split mono. And a split mono plus an epimorphism. So this means an isomorphism. Which means what happened? Like this is an isomorphism followed by an inclusion, which means F is a mono. So we assumed it is not an epi and we proved it is a mono. So either it is an epimorphism or a monomorphism. Okay, so our search for these nice morphisms, irreducible morphisms, is actually very simple. Any questions? Okay. So, sorry, just for the first page, I'm going to keep switching between these two. Right. So now, again, look at this. Now, once we know what an irreducible morphism is, can we get hold of more irreducible morphisms? The answer is yes. We can simply say that lambda f is also irreducible. Yeah, I mean, there is a typo here. If f is irreducible, then so is lambda f for any non-zero lambda.
I have a
Yes.
small question here.
Yeah.
So, in the view of studying the representation theory, and are we going to assume x and y are irreducible spaces, or it's just any spaces? I mean, any representation.
These spaces, we are not talking about spaces at all.
That is true. That is true. But can there be?
Mhm.
Can there be a map, irreducible maps between non-irreducible or non-indecomposable spaces also?
Yes. I mean, you are talking about spaces, but I will say objects. Yeah, let's just be more precise. Yes.
Okay.
So we'll come back to that eventually. Yeah. Right. So, right. So if f is irreducible, then all non-zero scalar multiples of f are also irreducible. Okay. And let us look at some irreducible morphisms. So here is an example. Yeah, we have taken the example of A2. Hopefully, everybody remembers from the first week that there are only 3 finite dimensional indecomposable objects. Yeah, you saw that from the proof of Gabriel's theorem. Yeah, they correspond to roots, positive roots of this, and there are only 3 roots. So you have dimension vectors 0, 1, 1, 1, and 1, 0. And I have shown you the morphisms. Now, it's a simple enough exercise to verify that this inclusion of 0k into kk is actually irreducible, and so is the other surjection. Okay. You take any of its factorization and you have to use that these are the only indecomposable morphisms. I will right now, I will only give you a sketch of the proof, an oral sketch. In the tutorial, we are going to see everything very clearly. Okay. So, or sketch of the proof is that if it factors through something else, then that something else is actually a finite direct sum of copies of these 3 morphisms. But you can't really factor the first map 0k to kk through k0. Because the second entry is 0, whereas in this morphism, k to k is an identity map. Yeah, this map is an identity map. So therefore, you can't really factor it through the third one. And therefore, you get the conclusion that it should be either split mono, the third one, the middle object, there should be a split mono or a split epi. Okay, so both these maps are.
No, I didn't follow the. I didn't follow the example. Can you repeat it again, please?
I will do it in the tutorial properly. Yeah, for all ANs,
no,
in fact.
You say both the maps are irreducible, but what are the two maps? I see only one, right? Oh, okay.
No, there
Between
are two maps. There are two maps.
right.
0k to kk and kk to k0.
Fine. I get it. Thanks.
Okay, good. Okay, so basically, if we understand that indecomposability of objects is similar to irreducibility of morphisms, yeah, no further decomposition or factorization possible, then we have to record this data in a diagrammatic form. This whole area is full of beautiful diagrams. So that is what we are going to do. Yeah, the so-called Auslander-Rayton quiver of a quiver Q. Yeah, so this is a new quiver that we are generating out of the given quiver. So this has as vertices the isomorphism classes of indecomposables. Yeah, we don't want to take multiple copies of the same object, essentially same object. And arrows are essentially like a basis of irreducible morphisms from one object to another, one vertex to another. A basis, yeah. This whole thing, I will take at least 2-3 lectures to formalize the notion of counting the arrows from one vertex to another. But I just want to give you a bird's eye point of view in the beginning. Okay, so you have to draw m arrows from the isomorphism class of x to the isomorphism class of y if there are at most m linearly independent irreducible morphisms from x to y. So in this way, we actually capture some kind of skeleton. Yeah, so this, if your quiver is of finite representation type, then we have captured the entire category rep KQ via this. Okay, how I will explain it, but this is a skeleton, so it basically encodes generators and relations for the module category. Okay, that's the idea behind this Auslander-Rayton quiver. However, what it fails to capture, yeah, I mean, this is not a complete picture. So basically, you can imagine, like, if it's forming a quiver, then that quiver will have an underlying graph, underlying simple graph, underlying graph, yeah, not necessarily simple because there could be multiple arrows. But that underlying graph may or may not be connected. Okay. So if there are two objects in different connected components, then any morphism between them, any non-zero morphism between them is actually a transfinite composition of these irreducibles and their sums. So that data is not captured by the Auslander-Rayton quiver. However, it's a good first approximation for the module, for the category of representations. Any questions?
Yes, can I ask a question?
Yeah, sure. Just go ahead.
So you're saying that you draw m arrows from x to y if there are at most m linearly independent irreducible morphisms from x to y. But I am not understanding the word at most here. Like,
yeah,
how many
I
arrows
will
will be
make
there?
this clear. Yeah, see, I'm going to like this first lecture, at least first hour, is all about giving you an overview of what is yet to come. Okay. I will make this everything very precise. Yeah, I don't expect you to follow everything, but just about the idea. If you have any questions, then I'm happy to answer.
Thanks.
I have a question.
Yeah, sure.
Probably this is a very vague question, but as you have defined irreducibility of morphism, so
Mhm.
so I mean, I don't know. Is this is this the same as the term simple in terms of category? Like, I don't know. Can we
Simple.
consider something called two categories of quivers and then simple morphisms maybe, and those they turn out to be the irreducible morphisms?
Okay, I don't know any two category of quivers, but this is I'm talking about the module category. Okay, here the category of representations. Sorry, not module category, but the category of representations. This is our category, main category, yeah, Rep KQ. And I'm saying certain morphism in that category is simple, is irreducible or not. Now, whether some author uses the word simple or not, I don't know.
Yeah, sorry. I mean the whatever two categories. There are two category of representation of quivers. I mean, is this irreducibility, this term irreducibility related to simpleness in terms of category theory? Uh,
Simple, no, I don't think so. See, this particular term, irreducible morphism, as far as I have seen, it's only restricted to Artin algebras.
okay, okay.
Yeah, so I don't think there would be a more general version. However, this notion could be there. Yeah, like only non-trivial factorizations are allowed. Yeah, that could be the case.
All right. Okay. Okay.
Okay,
Okay.
fine. Shall we go ahead, or do you have any
Sir,
more questions? Yeah.
yeah, I had a question. What did you mean that if you have two objects which are in different connected components, then they can be like written as a transfinite composition?
I, I will show you some pictures later on. Yeah, Auslander right and Quiver need not be connected. And therefore, you will see that, yeah, I will give you all these examples. This is just an overview. Yeah, if two things are not in the same connected component, then there might be some morphisms which cannot be written as a finite compositions of finite sums of irreducible morphisms. You have to talk about some infinite compositions. Yeah, that all I will make this precise.
Can I ask you one last question?
Yeah, sure.
Can you go to the previous page?
Sure. Yeah.
Below the green color graph, is that the
Okay.
AR Quiver for A2?
Yes. Yes.
So it's just have a 3 vertices and it's just the A3 looks
Yes.
like it.
Thanks for pointing that out. This is the Auslander right and Quiver. It has 3 vertices and only 2 non-trivial arrows.
Okay.
And that's all. Yes. I forgot to mention that, so thanks. Okay. So now here is the next classification problem. Yeah, we dare to ask this. We had a classification problem for the category of representations. Now, how hard is it? If it is very, very easy, then you call the algebra a finite representation type algebra. If it is moderately easy, then we call it tame. Yeah, we are treating algebras as, quivers as animals. So they are either finite, and finite is not related to animals, but tame and wild are. And the tame class is further subdivided into domestic and non-domestic. Okay, so all the zoology terminology is being used here. So yeah, this depends on the hardness or complexity of the classification problem one. Yeah, we had to classify quivers into one of these types. Now, for quivers, Upendra has already done this job for us. Yeah, what is the name of the theorem? Gabriel's theorem. So he already classified them into these 3 types. So they only finitely many vertices in the AR quiver, which translates to only finitely many indecomposables up to isomorphisms. Okay. So this problem, this classification problem 2, is based on counting. So he showed you that for quivers, this is precisely the ADE type quivers. Yeah, nothing else is finite representation type. Then tame means it is not finite representation type. However, we have enough control over this particular variety of representations for a fixed dimension vector. Again, I will make this definition precise in the last lecture. Yeah, not right now. But it basically says that you have sufficiently good understanding of what is happening here. And then suddenly there is the third one, and third one somehow calls one particular quiver as the villain. That is the prototypical example of a wild representation type quiver. And that is this Kronecker quiver K3. Yeah, only 2 vertices and 3 parallel arrows. As soon as your category of representations for a given quiver contains the category of representations of K3, then it becomes a wild quiver. However, it can be shown that as soon as your quiver is wild, then rep KQ also embeds inside rep K3. So there are embeddings in both directions. So they are all equally bad. Yeah, there is nothing is worse than the other. So the embeddings that I'm talking about, the technical term is representation embedding, but they are equally bad. So finite and tame are what we hope to classify. There are some Polish people here, and Polish people, I think, believe that even wilds can be classified properly. Yeah, at least I have one friend and who does that kind of work. But normally, representation theory of quivers is restricted to finite and tame. You want to understand what happens there. However, now you might ask me, because of Gabriel's theorem, which was proved back in 1980s, this problem is completely done using quadratic forms. So what else remains to be done? Right? So, well, I will tell that to you in a second. However, like these two, there is a proper definition of tame representation type and there is a proper definition of wild representation type, which is this basically. Yeah, whatever I wrote. There was this surprising result by Drost, and I think there was some error in the proof which was later on corrected by Crowley-Booby. You have already seen this name, Crowley-Booby, earlier. So this trichotomy theorem that every quiver lies in exactly one of these 3 classes. You don't have to worry about any other thing. Yeah, so this is a very powerful result. Because the definition of wild representation type is not that it is not finite tame representation type. It has its own definition, tame has its own definition, and then surprisingly, those are the only 3 things you can do. Okay, so this trichotomy result is a very powerful result in this area. So here is our first goal. Yeah, we have to replace the word quiver by a finite dimensional associative K algebra. Yeah, so quivers have an associated algebra, which is the path algebra. We'll see that soon enough. So the path algebra is a finite dimensional associative algebra if the quiver is acyclic. So if you remember, we were only talking about acyclic quivers mostly while talking about Gabriel's quiver. Yeah, ADE types are like that. Then yeah, maybe I mean some ideas also work for infinite dimensional things, but in this week of the course, we are going to be interested in only finite dimensional associative K algebras. I will also define a K algebra, yeah, if you don't know what it is. But if you are present this morning, then Venkatesh already did that for us. He was talking about associative algebras. Okay, so we are going to replace it with that. And this is the presentation aspect. This is what Gabriel brought into picture. Yeah, that quivers with something called relations. Yeah, we will define that as well. So bound quivers are presentations for all finite dimensional associative algebras. So quivers are actually diagrammatic way of encoding the generators and relations. Yeah, so that's why I'm emphasizing on the word presentation. The word representation is quite frequently used, but presentation is only used in the context of groups. Yeah, the presentation of this particular group, what you have generators and relations, right? So here we are talking about presentations of finite dimensional associative algebras. Okay. So that's our first goal. Then the second goal is that we have to talk about something called the radical of a module category. So normally, if you are thinking about a ring, then you know what the radical is. Radical of a ring. Then similarly, you know what the radical of a module is. And they are like, what is it? Like, can somebody say that? I'm sure people are competent enough to know the radical of a ring. Yes, somebody? Jacobson radical, have you heard of that?
Yeah, it's intersection of all left ideals. And it,
intersection of all?
Left ideals, which will also be an intersection of all right.
Of all left ideals, that would be zero.
Maximal ideals.
Exactly. Intersection of all maximal left ideals or equally intersection of all maximal right ideals. So that is the way we define it. But then this is an ideal itself. Radical is an ideal, specific kind of ideal. So what I'm saying is that even for an abelian category, we can define the notion of an ideal. It will have similar thing that it should be locally a subgroup, which means in home set, in each home set, it should be a subgroup, and it should be closed under, it will be a two-sided ideal. So it should be closed under compositions from either side. Yeah, so we'll properly define ideals in a category and we will define the radical, show that it is an ideal. And then using the radical, we will make precise the idea of how many arrows are there from one vertex to another vertex. So radical is going to be the key. Now, just like you have any ideal like ideals of a ring have got three different operations. One is intersection. Then the second one is addition. With respect to these two, it becomes a lattice, like the lattice of ideals. And there is a third operation which makes it a multiplicative lattice, namely the multiplication of ideals. So in particular, we can define finite powers of ideals. If I is an ideal, then I square, I cube, and so on and so forth. That forms a decreasing chain. In case of module categories also, you can define powers of the radical. And not just finite powers, but in fact, infinite powers. And those infinite powers can be indexed by ordinals. So for every ordinal beta, there will be rad to the power beta. Yeah, I will discuss all these things as well. And if something lies in a finite power of radical, then that morphism has a finite factorization in terms of irreducibles. If it lies in an infinite power of radical, but not in any finite power, then it can be written as a transfinite composition of morphisms. Yeah, that like just to give you a bit more idea about what is yet to come. Okay, I will make all these ideas precise, but this is our second goal, to make the idea of irreducible morphism very precise and the concept of the Auslander-Ruyten quiver. Any questions? Okay. So here we have started talking about the representation aspect of this representation theory. Yeah, the goal one that was related to presentations of finite dimensional algebras, whereas goal 2 and goal 3 have to do with representations. So this goal 3 is about Auslander-Rayton theory, which is really speaking the main goal of this lecture series. So here the concept of an almost split sequence. Yeah, if you know what a short exact sequence is, then short exact sequences are always the best. Yeah, like you understand everything about them. If you just know one or two terms, then you understand everything about them. Am I still audible?
Yes.
Yes.
Okay. Yeah. So I think people stop moving in their cameras, so therefore I had to ask. Yeah. So Auslander-Rayton theory and Auslander-Rayton, like this whole thing is based around the idea of the next best thing. Split sequences are the best ones, and almost split sequences are the next best thing. So we'll make this idea precise, and then in the Auslander-Rayton quiver, we can see some movement, some translation, and reverse translation. So all those movements can be captured using some techniques of homological algebra. So we will do all those things, and the epitome of all those, all the theory is the so-called Auslander-Rayton formulas, where we can capture the group of extensions between two modules using home sets. Yeah, so some surprising thing. Well, I'm uttering the word surprise. However, yeah, this is related to goal 1. That studying modules over finite dimensional algebras is essentially the same as studying representations of bound quivers. The word essentially the same actually refers to Morita equivalence, which means their module categories are similar, are equivalent. And bound quivers means quivers with certain relations. I will explain what they are when the time is right. And therefore, we can interchangeably use the word representation or a module. And we have captured all finite dimensional associative algebras in this way. Okay, so there are multiple benefits of this way of doing things. So we have a beautiful diagrammatic presentation for the algebra. Then we have beautiful skeleton, first approximation of the module category in form of Auslander-Rayton quiver. And we can say a lot about those Auslander-Rayton quivers in terms of Auslander-Rayton theory, translates, and so on. So basically, this whole idea came into existence through two different schools. The first one, you have seen Gabriel, and he introduced this quiver theoretic approach. And the second school is the so-called Auslander-Rayton school of thoughts. So here we are going to, the main idea is, of course, the almost split sequences, but the tools will be homological in nature. Okay, so any questions so far? Okay, so I will be using the words representations and modules interchangeably. And let's go to the third page then. And I will talk about examples as we go along. Okay, so what are associative K algebras? Well, this entire week is essentially a crash course on this whole material. But here is a smaller crash course on not necessarily commutative algebra. Okay, I'm not going to prove any of these results. If you haven't seen these things, these are standard results. You can just go and check them in any algebra book. But my main emphasis will be on setting up the notation, convention, and looking at specific examples. So an algebra is any group which is also a vector space, K vector space. So any K vector space really, which has a binary operation. Now, if that additional binary operation happens to be associative, then you call it an associative algebra. I'm not going to use anything else apart from associative algebra, so I will stop saying the word associative. Yeah, there are no Lie algebras in picture. And the vector space structure and the multiplication structure, they have to be well behaved. So this identity must be satisfied. If lambda is a scalar, then lambda AB is lambda A B or A lambda B. Now, this is the compatibility relation between them. And all our algebras will be unital. They will have a multiplicative identity. You will soon see why. And 0 is not equal to 1. So they contain at least 2 elements. And what will be the dimension of an algebra? Well, it's dimension of the underlying vector space. The multiplication structure does not play any role over there. And what is the homomorphism between them? It is a unital K algebra homomorphism, which means it should preserve 0, it should preserve 1, addition, multiplication, and scalar multiplication. So it's a K linear map, which is also a ring homomorphism of unital rings. Okay, so these are some simple enough examples. So K, Kx is the polynomial ring in two variables, in one variable. Then Kxy is the polynomial ring in two commuting variables. And K bracket, angular bracket xy is the polynomial ring in two non-commuting variables. If you attended morning lecture, then this is tensor algebra in two variables to generate two basis elements, yeah, x and y. So the polynomial, the monomial xyx is different from x square y over here. So this is also a K algebra. Then MNK, the matrix ring, matrix algebra. You can add and multiply matrices and also scale every single entry by a scalar. So therefore, this is an algebra. And inside matrices, many things go and sit. So namely, UNK, the upper triangular matrices, LNK, the lower triangular matrices, and some other things as well. Yeah, lower triangular, upper triangular, we usually have the habit of using these notations. But observe this particular thing, particular sub-algebra of the lower triangular matrix algebra. Oh, no, sorry, the matrix algebra, just the matrix MNK. So where I'm writing K to mean anything non-zero is allowed. Sorry, this entry has to be, this A33 has to be K. Yeah, that's a right-o, not a typo. I will correct that before sending you the notes. Yeah, so this third 3x3 entry has to be K. So all the diagonal entries are Ks, and then these two off-diagonal entries can be non-zero. So this is the collection of all such matrices. And you can verify, I mean, addition is not surprising, scalar multiplication is not surprising, but this particular way of putting only 1 0 at second row first column position, that still retains multiplication. Yeah, very surprising thing. This is also a ring. This is also closed under multiplication, right? So let us do some simple thing. Which ones are infinite dimensional amongst these? Can you please tell me? Which ones are infinite dimensional algebras?
Kx, Kxy, Kxy generated by xy.
Okay, so these three and what else? Anything else? No. Just these three are infinite dimensional, right?
Yes.
Okay, keep that in mind that these three are infinite dimensional, the rest are finite dimensional. And I'm sure you can all compute the dimensions in case it is finite dimensional. Okay. Now, just like rings, yeah, we also have for algebras this opposite multiplication operation. So if A is an algebra, then we can take the opposite algebra, where we simply take A multiplied by B in the opposite algebra, it's just B dot A. Yep, something simple. Yeah. If it is commutative, then it doesn't matter, but non-commutative, it does matter a lot. And this is a standard result now that because our algebras are unital, so Zorn's lemma guarantees the existence of maximal ideals, maximal left ideals, maximal right ideals. Without having unity, we may not have maximal ideals. So we are assuming existence of one other than zero for using this particular result. We need existence of maximal ideals. Okay. And then the Jacobson radical, we already discussed that, is simply written as the intersection of all maximal right ideals. However, right, left doesn't really matter. So here are some equivalent criteria for an element to belong to the Jacobson radical. I'm not going to cover the proof. This is standard stuff. So for any element A belongs to each maximal right ideal if and only if it belongs to each maximal left ideal, if and only if A minus AB has a right inverse for every B. And if and only if, I mean equivalently, if and only if 1 minus AB is a unit, which means it has a two-sided inverse. So this is an equivalent characterization of the Jacobson radical. And then you can write down 2 dash and 3 dash, I suppose. Yeah, the left versions, right versions. And Jacobson radical, as a consequence of proper, like these equivalent conditions 1 and 2, it actually becomes a two-sided ideal. Okay. So this is the first corollary, that JA is a two-sided ideal of A. Two-sided ideals are good because then we can take the quotient ring or quotient algebra. With one-sided ideals, we just have a
But
set
will be
of
three.
quotients.
What will be
Yeah.
3 dash? What will be 3 dash? Because there is no left right. We are saying just element 1 minus AB is unit. So but then 3 dash.
Yeah, you can still see some asymmetry in there. For all B, the element 1 minus BA is a unit.
Okay.
Yeah, not AB.
Okay.
Yeah, so that's why I did not write that. Okay. So because it's a two-sided ideal, then what will be the Jacobson radical of the quotient? Well, it is simply 0. And whenever we have a two-sided nilpotent ideal, then it is contained inside the Jacobson radical. So this is, I mean, Jacobson radical itself could be nilpotent, and that is what we are going to see. The next theorem, which is a standard result again, that if I is a nilpotent ideal such that nilpotent two-sided ideal, yeah, this triangle notation actually denotes that it is a two-sided ideal. If it is a nilpotent two-sided ideal such that the quotient algebra is isomorphic to k to the power n, then I is actually just the Jacobson radical. It can't be anything else. It is the maximal possible situation. Any questions so far? Yeah, we are going really fast at this point. Okay. So now we can come to the concept of representations or modules for these associative algebras. Again, some notations. A mod is the category of left A modules. Mod A is the category of right A modules, and both these categories are abelian. They have all the nice properties. And if A is assumed to be a finite dimensional algebra, then actually it is an Artinian algebra. Artinian algebra means ideals satisfy the descending chain condition. So which also implies that it is Noetherian. Yeah, that's a famous result in rings. Yeah, ring theory. That Artinian rings are Noetherian rings. And in particular, one simple consequence of Noetherianness is that A mod, the category of finite dimensional left A modules, is an abelian category. In general, for a given ring, that is not necessarily true. Okay? Having this particular property is not true. In general, kernels are missing from this finite dimensional module category, or finite dimensional is equivalently finitely generated, equivalently finitely presented, if you know these terms. So these finitely presented modules over a general ring, they do not necessarily form an abelian category unless the ring is coherent or Noetherian or Artinian in this case. Yeah. So we have this nice property and we are heavily using it in this theory. I'm not going to explicitly utter it, but the abelian property will be used. And mod A is the category of finite dimensional right A modules. Same notation, A mod and mod A. Whichever side I write A on, that is the left right. And well, if you have seen some enough categories, then or even enough algebra, then left A modules are nothing but right A op modules. Yeah, so we can equally keep studying only the left modules. Yeah, this result says that. This duality says that studying left modules or right modules, studying left or right modules for all algebras is same as studying only left modules for all algebras. But for a particular algebra, at least in our lectures, we are only going to talk about the left modules. Yeah, I'm making that particular convention because of the way I will be writing paths. We'll soon come to paths, and I'll show you what is needs to be done there. Okay, so A mod, A mod is same as mod A op, left and right modules. And this Nakayama lemma, which is again a celebrated result in algebra, it implies that if you have a finite dimensional algebra, then JA is nilpotent ideal. So the radical is nilpotent. Where are we going to use all these things? Well, in this particular case of a local algebra. Again, something very standard. Local means that there is a unique maximal ideal, but which one? Yeah, left or right? So here we are going to say that, well, it doesn't matter whether left or right. It just has a unique ideal. They are equivalent, having a unique maximal left ideal, having a unique maximal right ideal, and the set of non-invertible elements forming a two-sided ideal. And this one as well. Yeah, fifth property is also interesting, that every element is either a unit or 1 minus A is a unit. So basically all the units, they form the complement of JA. Or look at the fourth property, it says that A mod JA is isomorphic to a field. Now, which field? Well, we don't know. It's just isomorphic to a field. This already implies that this is maximal. But which field, it doesn't matter. However, if our field is algebraically closed and A is a local K algebra and it's a finite dimensional algebra, then A mod JA, which was just isomorphic to a field, that field has to be K. It can't be anything else. Here we have to use that the field is algebraically closed. Without that assumption, we cannot get the conclusion. Yeah? And therefore, the only idempotents in the local algebra are 0 and 1. Do you understand idempotents? The elements whose square is itself. I have one more slide about idempotents. Well, okay, so we'll end this discussion with a simple criterion for indecomposability. If I'm given a module over a finite dimensional, over an algebra over an algebraically closed field, yeah, that's our base assumption, then a module is indecomposable. Yeah, indecomposability, as you remember, I hope that indecomposability is very crucial thanks to Krull-Schmidt property. That we need to identify all finite dimensional indecomposables. Well, how are we going to detect whether a given module is indecomposable or not? So here are two criteria. The first one is that, it's the third one on the list, that the endomorphism algebra, which means the collection of homes, like collection of morphisms from M to M, that is a local K algebra. And the second property is that if you subtract an appropriate multiple of the identity, then what remains is a nilpotent morphism. So scalar multiple of the identity morphism plus a nilpotent morphism. That's the form of every endomorphism. Any questions so far?
In the previous theorem, if we did not start with a algebraically closed field, would A mod J of A be? In the previous theorem, if we did not start with an algebraically closed field, would we get some result that A mod J of A is isomorphic to its closure, like to the closure of the field?
Yes, I think so. Yeah. I don't remember the proof right now, but yes. Okay, any other question? Fine. So I have prepared one more slide on idempotents, but I will come back to it. Instead of that, I will directly go to this topic, which is of particular interest for us. Yeah. And here I will actually start writing examples. So maybe I should stop sharing this particular screen and go to the other screen, yeah, where everything else is there. Hopefully the page is loading and okay, maybe it's creating some problems. Okay. Okay. This is what this is the main object of study. I was just doing the basics so far. So path algebras. Now you are given a quiver Q. Q0 is the vertex set, Q1 is the set of arrows, and S and T are functions from Q1 to Q0, which take each arrow to its source and target. So a path in it is either a zero length path, which means a lazy path, which we don't draw. Yeah? While drawing the lazy paths, we are also going to be lazy. Yeah? So we don't draw them. And while talking about this non-zero length paths, so these are sequences of arrows with length at least 1. Yeah, length is the number of arrows which appear in it. So let me write something over here, and we are going to do illustrations simultaneously now. The simple thing that I will do is maybe 1, 2, 3, and this is alpha, this is beta. So how many paths are there? Can you please tell me? All the paths, can you list all the paths?
2 paths. Alpha and
2
beta.
paths. Which 2 paths?
Alpha from, no, sorry, these are arrows. There is only one path from 1 to 3.
Why can't a length
paths, right?
one path? Yes, 6 is the correct answer. Can you please tell me what those 6 paths are?
First are the lazy paths. Means
Very
one
good. So I'm going to label them E1, E2, and E3. And then?
Between vertex 1 and 2.
Okay, what is the name?
Alpha is right, like you have.
Correct. Alpha. The second one.
Then beta.
And then the last one.
I don't know the order. Is it alpha beta or beta alpha? How should we
Yes.
take?
So I'm going to write it as beta alpha.
Okay.
Yeah. So this is the only 2 length path in this. So it is a 6-dimensional. Okay, the corresponding algebra will be 6-dimensional. Yeah, because there are 6 paths. So what is the source of beta alpha?
1.
1. Yes, and target of beta alpha is
3.
3. Okay, thank you. So this is precisely what I have written over here. Yeah, nothing fancy. A path is just a lazy path or a sequence of arrows with n bigger equal 1, such that their source and targets appropriately agree. The source and target of the lazy path is just the same vertex, and source of any other path is source of the first letter, and the target is the target of the last letter. The first and last concepts are relative, but they are this is my convention. I already showed you what the convention is. The path algebra has an underlying vector space generated by paths of non-negative length. Okay, so this is simply the underlying vector space of this path algebra. If this is my A3, this is actually my A3. So the dimension, the k dimension of KA3 is just going to be the number of paths, namely 6. And what does a general element of this look like? It looks like lambda 1 E1 plus lambda 2 E2 plus lambda 3 E3 and plus up to lambda 6 beta alpha. So these 6 sums. However, it's not necessary that there will be only finitely many paths. So for example, consider this quiver, namely the loop quiver. L1 for one vertex and one loop. Yeah, if this is my alpha, then can you please tell me what paths there are? This is my vertex 1. If you don't speak, I'm not going to proceed.
Many.
Yeah?
There'll be infinitely many paths.
Infinitely many, and which ones?
We'll start with the trivial one, like the lazy paths, and then alpha,
Very
alpha
good.
square.
Alpha, alpha square, okay. And dot, dot, dot. However, a general element of KL1 Yeah, so an element of KL1 is a finite sum. So lambda I alpha to the power I, but only finitely many are non-zero. Which means, in simple language, this is simply polynomials in alpha with coefficients from k. Okay, so this is the underlying vector space of Ka3 as well as KL1. KL1 is infinite dimensional, Ka3 is finite dimensional so far. Yeah. Now this is the underlying vector space, but we also have to describe the multiplication. So the multiplication of on KQ is defined on generators like this. So P dot P prime is the concatenation if possible. If concatenation is impossible, then we simply take the multiplication to be 0. So for example, here you can multiply in KL1, you can multiply anything by anything. Concatenation is always possible. The source and target is the same vertex 1. However, in Ka3, that is not always true. So for example, I can ask you over here, what is the multiplication of alpha times minus 5 beta plus E1? So minus 5 will come out. So alpha times beta, is it 0 or non-zero?
It is 0.
It is 0. And the second one, however, will remain because alpha times E1 is taken to be just alpha. So therefore, the final result is alpha. Here, everything can be multiplied with everything, and that will usually be non-zero. So that is our definition of the path algebra. And even though I use the letter like this point here, multiplication will be written juxtaposition. We won't write that point. And as I already mentioned, the general element of the path algebra is a finite k-linear combination of paths. And as you saw in this example, the dimension of the path algebra is finite if and only if Q is acyclic. So here I'm going to use the word acyclic in a very strong sense, that there are no directed cycles. Yeah, so is L1 an acyclic quiver or not? Is L1 acyclic or it has a cycle?
It has a cycle.
It has a cycle, yeah, namely it's a loop. It's a single loop. So Kronecker quiver K, it's written as this. You have alpha and beta as parallel arrows. Is this acyclic or not? Does it have a cycle? It is acyclic.
It is
Yeah,
also
because
correct.
yes. So we only look for a cycle formed, like just follow the arrows and then does there exist a cycle or not? That's all matters. And yeah, so this is a finite dimensional algebra. And what is its dimension? Four. Yeah, alpha, beta, E1 and E2 are the only possibilities. So it's a four-dimensional algebra. Okay. Right. Now, once we are, before I go any further, let us try to write these things in a nice form. Okay, so we have to have some kind of conventions, but because we have already chosen the convention for writing paths, the data of Ka3 can be written as lower triangular matrices 0, 0, 0, 0. Okay, so this is our Ka3. Ka3 is isomorphic to this. Do you understand what I mean by this? This is basically the location of E1. This is the location of E2. This is the location of E3. Then this is the location of alpha, beta, and beta alpha. And then there are no arrows from 2 to 1, 3 to 1, and 3 to 2. So therefore, all these quantities are 0. So the coefficients of all the generators, they can be written in a matrix format like this. And we will get this particular presentation of K3. Any questions about this?
Is this just the incidence matrix for?
Is it really the incidence matrix? Think again. Is 1 and 3 adjacent?
Okay, no, they aren't.
They aren't. Yes. Okay. So you got it.
I have a question over here. Like, for instance, so here you are meaning that an ijth entry of the matrix correspond to a path starts from I to J, right? But what if there are multiple paths from I to J?
Yes. So I was going to show you the next example. Yeah. So we already have an example here, Kronecker quiver. And over there, I write K, K, and K direct sum K and 0. Yeah, that's the way to write this. And the multiplication is defined appropriately. So the matrix notation is especially useful if there are no parallel arrows. Otherwise, also you can make sense of them by writing down the endomorphism modules and then the bi-modules in the other off-diagonal entries. Well, we can make it precise, but let's not get there. There was one more question.
You specified the algebras generated by paths of non-negative length.
Yes.
So does everything have non-negative length?
Sorry?
Don't all paths have non-negative length? Why do you need to specify
Oh,
that?
yeah, fine. It's just a way of saying, all paths have non-negative length, yeah. I mean, sometimes you can take convention that something is going backwards, etc., but these are all going forward. We'll, in one of the lectures, we'll see something where we also talk about some walks on a quiver. Yeah, and there we'll have paths going in the other direction. But so far, just this simple thing.
Yeah. So the main advantage of writing in the matrix notation is to concatenate or compose the elements in the path algebras, right? And maybe how do I compose a block or special matrices of the Kronecker Quiver type? Maybe
now there is nothing to compose. Yep. Only alpha composed with E1, beta composed with E1, or E2 composed with alpha, E2 composed with beta. Only those things make sense. The composition will make sense if and only if the corresponding matrix entries are compatible. Yeah, if at all they interact with each other properly. Otherwise, everything else will remain the same.
Okay. So this is a 2x1.
This is a 2 cross 2 matrix because there are only 2 vertices. So it will be a 2 cross 2 matrix. But some entries could be other modules, like modules other than K.
Okay.
Yeah, so vector spaces could have dimension any other finite dimension, not necessarily 1 or 0.
Okay.
And for the loop quiver, we are like this particular notation is useless. And I would like to show you one more orientation of A3. Let me call this A3 dash. And this notation is, just a moment, 1, 2, and 3. No, maybe I should do 1, 3, and 2. So I have something like this. And then if you count all the paths, then there are 5 paths, and this will be 0. 2 to 3, there will be this, and 1 to 3, there is something. And if you remember, I showed you this particular matrix algebra earlier. Yeah, let me go here. Yes, this matrix algebra. So that is actually the path algebra of A3 dash, A3 with this particular orientation. Well, in fact, let's do the other side now. Look at these things, yeah, and then tell me what will be the corresponding quivers. What will be the quiver for K?
That's just the trivial 1 dot.
Yes, this is A1. Yeah, A1. What about KX?
The loop.
The loop quiver. What about KXY?
That should be a quiver with some relation, because the 2 loops will get me K and
Very
bracket
good.
X.
Very good. So if you have 2 loops, so L2, loop quiver L2, that will give me K with angular brackets XY, and not the commutative version. Okay, so far what we have not covered is K square bracket XY. That can't be obtained as the path algebra. What about UNK?
Just you had now showed me A3, so it can be an AN with a different orientation.
Yes, reverse all the arrows in the standard orientation. Yeah, all the arrows should go from n to n plus 1, n minus 1, then n minus 1 to n minus 2, and so on. Then that will give me upper triangular matrices. And this one we have already seen, lower we have already seen. And MNK, the entire matrix ring.
That seems slightly trickier, because you need a path from I to J as well as J to I, and that will also create some loops. So I don't think
right.
That's also going to be something.
Okay, so keep this question in mind. Yeah, so far we haven't resolved 2 examples. One is K, the polynomial ring in 2 collect. Okay, I didn't want to show balloons. Yeah, if I do 2 there on screen, then balloons pop up. So the polynomial ring in 2 commuting variables and the matrix ring. These are the 2 examples we haven't seen. We don't know what to do with them yet. Okay, so by the end of tomorrow's lecture, you will definitely understand what is the resolution for both of them. And let me see if there is something else worth saying at the end of this lecture. No, I think I should stop here. And I will take questions if any.
This KXY, where these are angular bracket XY. This is one node with 2 loops. What is it?
One vertex with 2 loops. Yes, correct.
Okay.
Yeah.
Professor, could I ask a question?
Please go ahead.
So what if the 2 path algebras are isomorphism of the 2 diagram is isomorphism? So what is the relation between the matrix you write?
Okay, this matrix, you mean this matrix and KA3?
Yeah. If A3 and A3 prime is isomorphical graph isomorphism. So what is the relation between the matrix you write? Yeah.
Okay, so what I'm telling you is whatever multiplication is written here, yeah, this multiplication on generators in the case of ANs, yeah, the quivers of type AN, that can be abbreviated in terms of this, that you simply write down which arrow goes from which, like which vertex to which vertex. You simply note the coefficient of that over here. These are all the generators. And then this multiplication is exactly same as matrix multiplication.
Okay, thank you.
Okay. Any other questions?
For MNK, will we have some case where the underlying quiver is like a complete graph, but with some additional, because we need a path from both I to J and then J to I?
We will see. We will see. Yeah, I will choose not to answer this question today. I'll kill the surprise for tomorrow. Yeah. Anything else? Okay.